Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. This is Adib, your lecturer for statics, section 16 and 17. So here we're going to learn about chapter 5. We'll continue learning on chapter 5, equilibrium of a rigid body. So in the past, we have studied this conditions for rigid equilibrium, free body diagrams 2D, just a recap, equations of equilibrium, and 2 and 3, three force members. So I'm going to repeat this again in this recording, and then we'll go to the 3D, right? Why the color is yellow? Okay, next. So as we have seen before, the conditions for rigid body equilibrium. When we say equilibrium of a body, we have two conditions. Two conditions must be satisfied. The first one is this, which is the summation of forces equals to 0. The second one is summation of moment equals to 0. So we have to look at this. So forces is fine, Fx equals 0, Fy equals 0, Fz equals to 0, depending on your how many coordinate system that you have. So how about moment, M? So for moment, we have looked before that actually for the force vector moment, the equation is R arm vector cross with the Fr, the force. Okay, and then we plus with the couple moment, okay, equals to 0. So these two conditions must be satisfied. So for free body diagrams, we have to look at the support reactions. So basically for support reactions, we have two types of reactions, support reactions. The first one, if the support prevents translation, then basically a force is developed, okay, in that direction. If the support prevents rotation, then basically a couple moment is exerted on the body. So here we have this a couple of examples for cable, smooth pin, roller, and fixed support. These are actually the common types of supports. So you look one by one. For cable, see this cable. So this is basically the member. So it is supported by this cable with angle theta from the horizontal line. So if what we do is that for free body diagrams, as the name implies, we want to free the body from the supports, because we want to do the analysis. The summation of forces equals 0, summation of moment equals 0. So we remove the cable here. See, there is no cable here, and we have to exert force along the line of the cable with same angle theta from here. Why this is a line? Because it's cable. As simple as that. For cable support, then you just have one reaction, which is the force along that line, along the cable. Alright. Same goes to this weightless link. Alright. Same. So basically weightless link. So basically you have this the just one line of force support. Alright. And how about roller? If it is roller like this, there is always a force which is perpendicular to the surface. Alright, like this. You see, perpendicular force to the surface. And then if it is rocker, same. For the rocker, then there is a force perpendicular to the surface. Alright. Smooth contacting surface, again, same. One force perpendicular to the surface. Roller or pin in confined smooth slot, then basically same. You have the one normal force perpendicular to the surface. And if it is a member pin, this is member pin. Connected to the collar, this is collar, okay. On smooth road, this is the road. So basically for this member pin, the force reaction will be perpendicular to this collar, okay. This is the collar, right, like this, okay. Okay, we go on with the smooth pin. Okay, so this is another common type of the support reaction. For smooth pin, basically we have to resolve into fx and fy. Why is that so? Because actually there is a resultant one. You see, if you sum them up, the vector fx, vector fy, then you get the vector fraction f. Why we do fx and fy? Because actually this is x and y. We'll look at this the same problem later for smooth pin in 3D. That actually you have to resolve into fx, fy, and fz, because that's for 3D. This is for 2D. For 2D, you just have fx and fy. All right. Same like this before. We have seen the member fixed connected to collar. This is the collar. Okay, on smooth road. So basically, you have one force here, normal, and then you have the couple moment. All right. Okay, for fixed support, this is another type of support reaction, which is very common actually. For the support reaction, just bear in mind that you have these two fx and fy like before, like the smooth pin, but you have additional couple moment here. All right. So there are 3 unknowns. So for instance, for this free body diagram here, this is a car's engine. All right. So you have the two, let's say in 2D, then basically you have two chains, let's say, connected to the hook here. So basically, if you want to draw the free body diagrams here, so basically you have the weight of the engine acting at the center of gravity. This center of gravity we learn in chapter 9. And then you see what we do is, we know that there is a weight going downwards, pulled by the gravity, isn't it? And then we remove the constraints. The two constraints here are these two chains. So we remove these two chains, and then we substitute the chains with the reaction forces, which is T1 and T2. Why only these two forces? Because this is like a weightless link, right? Or like a cable. Okay, we continue with the free body diagrams. So the procedure for drawing free body diagram, first we draw the outline shape. You can read on your own the details. Then show all forces and couple moments, and then we identify each loading and give dimensions. So for instance, this cantilever beam. Okay, this is cantilever beam. It is loaded here 2 meters from the fixed support. You see, this is a fixed support. So what we have to do is that we have to first draw the outline shape. So this is the outline shape. You see the blue one here. Okay, this is the outline shape. So don't just simply draw a line. It's not enough. Sometimes it's misleading. So better to draw the outline shape. So basically, what does it mean by that is that we draw the outer line, outer body. All right. And then after we draw the outline shape, then we show all forces and couple moments. So what is the obvious force, which is the first one here, isn't it? The concentrated load acting at 2 meters from the support A. So we draw 120 Newton here, right? And then what happened here? What happened at point A? Why doesn't the beam going down when we apply 1200 Newton load? It is because it's simple. It's because we have the fixed support here. So there will be 3 types of reactions. The first one is the horizontal force, vertical force AY, and then the couple moment MA. Alright. So and then what we have to do is identify each loading. This is the concentrated load, AX, AY, MA due to the fixed support at A, and then we give the dimensions. Dimensions are given from here, which is 2 meter from the support, and then 3 meter. Oh, there is another one, which is the weight. Alright, so because this is a cantilever beam, it has a weight, unless the question tells you to neglect the weight, then you have to include the weight. Alright, so there is a weight W. So where is the location of the weight? The weight will be in the middle of the line. Line of the beam is 6, so it is 3 and 3 in the middle, right? So again, as a recap for point A here, the fixed support here. Fixed support cannot move, cannot rotate. That's the reason why cannot move. Then it doesn't move in X, it doesn't move in Y. Okay, in the horizontal and vertical direction. So that's why we have AX and AY. And the fixed support cannot rotate. So that's why you have the couple moment MA. Okay, if it is a pin, then basically cannot move. It has AX, AY, but it can rotate. So there is no MA for a pin. Alright.